Hello, I'm Sebastian. Welcome to 9R Trees podcast. Today, I will summarize and review the book. QED, The Strange Theory of Light and Matter, is Richard P. Feynman's famously approachable introduction to quantum electrodynamics, the theory that explains how light and matter interact. Adapted from public lectures, the book aims to show what QED is about without heavy mathematics, while still preserving the logic that makes the subject intellectually honest. Feynman guides readers through a world where particles behave like events and probabilities, and where the most accurate predictions in science come from adding contributions from many possible histories. Along the way, he introduces the diagrammatic thinking that now bears his name, not as a technical tool for specialists, but as a way to visualize interactions and keep track of what can happen. The result is a compact, engaging account of why everyday intuition fails at small scales, and how physicists nevertheless compute answers that match experiments with astonishing precision. I will give you key takeaways from this book. Firstly, from common sense to quantum sense, Feynman's starting point is the gap between ordinary intuition and the behavior of light and electrons. Instead of treating physics as a pile of formulas, he frames it as a set of rules for predicting outcomes, emphasizing that quantum theory is not merely strange, but precisely structured. The reader is led to rethink what it means for something to happen, since at microscopic scales you cannot reliably assign a single classical story to an event. Light is not simply a wave or a stream of particles in the everyday sense, it is described by probabilities that can reinforce or cancel. This shift helps explain why phenomena like reflection, refraction, and scattering are best understood by considering many alternative possibilities rather than one definite path. A key lesson is that the goal is not to rescue intuition, but to replace it with a new kind of intuition rooted in the quantum rules. The book's appeal is that it does not demand advanced math to appreciate this transition. Instead, it uses clear reasoning and concrete examples to show how quantum thinking departs from classical pictures while still producing reliable, testable predictions. Secondly, probability amplitudes and the idea of adding paths. One of the central ideas presented is that quantum predictions are built from probability amplitudes, quantities that combine like arrows in a plane. Instead of adding probabilities directly, QED tells you to add these amplitude arrows first, and only then convert the result into a probability. This simple rule creates the distinctive quantum effects of interference, where different alternatives can cancel each other out or amplify each other. Feynman uses this framework to build an accessible version of the path integral viewpoint. Light and electrons can be treated as if they explore many possible routes, with each route contributing an amplitude. Even when a single path seems most reasonable, the correct prediction arises from the combined contribution of nearby alternatives. This approach provides an intuitive handle on familiar optical effects, making reflection and refraction outcomes of constructive and destructive interference across many histories. The emphasis is not on deriving equations, but on understanding why the rules take this form and how they differ from classical probability. By focusing on amplitudes and their addition, the book equips readers with a conceptual toolkit that can be reused whenever quantum phenomena seem paradoxical. Thirdly, photons, electrons, and how interactions are counted, QED explains how light and charged particles influence each other through discrete interaction events. Feynman discusses photons as the quanta associated with electromagnetic interactions and shows how thinking in terms of emission and absorption events clarifies what it means for light to affect matter. A major theme is that quantum theory does not give a single storyline of what happens between preparation and measurement. Instead, it provides a procedure for calculating the likelihood of outcomes. In this view, the electron is not a tiny billiard ball following a known trajectory, but a quantum object whose interactions with light and other charges are summarized by well-defined rules. Feynman also introduces the idea that calculations are built from contributions of different interaction patterns, each with its own amplitude. Some processes are simple and dominant, while others involve additional intermediate interactions and contribute smaller corrections. This sets up the logic behind approximation in quantum field theory. You can often get very accurate results by including the most important contributions and then refining the answer by adding more complex ones. The discussion gives readers an appreciation for how QED organizes complexity without requiring them to learn the full technical apparatus used in professional computations. Fourthly, Feynman diagrams as a visual language for QED. A signature contribution associated with Feynman is the diagrammatic method for representing particle interactions. In the book, diagrams are presented less as artwork and more as a bookkeeping system that matches the underlying quantum rules. Lines and vertices correspond to particles and interaction events, and different diagrams represent different ways a process might occur. What makes this powerful is that it turns an abstract calculation into a structured inventory of possibilities, where each diagram contributes an amplitude and the final prediction comes from combining them. The diagram language also conveys why certain effects are rare. Adding extra interaction steps typically reduces the contribution, so more complicated diagrams often matter less, though they can become important for high precision. Feynman's exposition helps the reader see that diagrams are not literal pictures of particles traveling through space like tiny projectiles. They are symbolic representations of terms in a calculation. This distinction prevents a common misunderstanding while preserving the intuitive value of the diagrams. By learning what diagrams mean and how they guide reasoning, readers gain insight into how modern particle physics communicates and computes, even if they never perform the full calculations themselves. Lastly, accuracy, renormalization, and the meaning of physical constants. QED is celebrated for its extraordinary agreement with experiment, and Feynman uses that success to discuss what it means for a theory to be both strange and trustworthy. He highlights that the theory's predictions depend on a few measured constants, such as the electric charge, and that once these inputs are fixed, the framework can produce extremely precise numerical results for many phenomena. This leads naturally to the issue of infinities that appear in intermediate steps of calculation. Rather than treating this as a fatal flaw, QED handles it through renormalization, a systematic way of relating the parameters in the equations to the quantities actually measured in the laboratory. Feynman's treatment aims to convey the logic without heavy technical detail. The theory is set up to compute observable outcomes, and the values used in the computation are those defined by measurement procedures. This topic also raises philosophical questions about what counts as an explanation in physics and how far a model can be trusted when it uses non-intuitive mathematical machinery. The reader comes away with a balanced view. QED is not a comforting narrative, but it is an exceptionally effective predictive tool, and its success reshaped how physicists judge the adequacy of fundamental theories. In conclusion, this book is best suited for curious non-specialists, science-minded students, and engineers or programmers who want a concept-driven understanding of quantum ideas without committing to a full textbook. It is also valuable for readers who have encountered popular accounts of quantum mechanics and want a more disciplined explanation that still stays readable. The benefit is practical as well as intellectual, by learning how probabilities are built from amplitudes, how competing alternatives interfere, and why interaction diagrams organize calculations. You develop a new mental model for uncertainty, prediction, and evidence. That model can sharpen critical thinking beyond physics by reinforcing the difference between storytelling and rule-based inference. Compared with many similar books, QED stands out because it is written by a central figure in the subject who is determined to be clear about what the theory says, what it does not say, and how physicists actually compute. It avoids empty mystique while preserving the real strangeness. You are not buying a catalog of fun facts. You are buying a compact guided tour of one of the most accurate theories ever built, presented with uncommon clarity and intellectual honesty. If you would like to support Richard P. Feynman, you can buy the book through the Amazon link I've provided in the podcast description. After reading the book, please let me know what you think and share your thoughts. See you around.